Hello everyone, my name is Anjan Choi and welcome to Lab Report 3 Circuits for Physics 2212. Here's the table of contents. The goal/purpose is to predict the behavior of circuits containing resistors in series and parallel. Use multimeters to measure the actual values of conventional current and potential differences in the circuits and examine the behavior of ohmic resistors and capacitors. Some assumptions is that we're doing this in ideal conditions and there's no energy loss. Concepts/fundamental principles is the conservation of charge and energy, Ohm's law, electric potential, capacitance, and charge storage, and exponential change and time constants. The preview of the lab results is that we can predict the behaviors of circuits containing resistors in series and parallel. We can measure the actual values of conventional current and potential differences in the circuits. We can examine the behavior of ohmic resistors and capacitors, and however, behaviors for circuits are different for ideal and realistic scenarios. So the method that we're doing is that we're using a simulation on a computer and we're adding circuits, wires, resistors, capacitance, ammeters, or voltmeters to recreate the flow of current, and then predict the behaviors of the system. So for part 2 that we have for charge conservation, energy conservation in series circuits, for 2.1, which is to predict the current I1 and I2 that would be measured by the two ammeters, we just simply do I is equal to volt over resistors, in which, since this is a closed system, I1 is equal to I2, in which it is equal to 0.020 amps. Here, as we can see, were my predictions correct? Absolutely for 2.2. For 2.3, reverse the connections to one of the ammeters. What does the ammeter read when inserted backwards? It is still read as 0.020 amps because the ammeters here are recorded as magnitude. For 2.4, we are describing the readings on both the 2 meters, explaining the new readings on both of the 2 meters. The voltmeter reads negative 3.0 volts and 0 amps for the ammeter right here. Note that the red here represents the high potential, black represents low potential, which explains the negative 3 voltage, and it is 0 amps because the system is open and the current can flow here. For 2.5, we're measuring potential difference, which is V minus VP. So V, B, C, D, E, F, G, and H. No, I actually did make an error here. So VF minus VD, this is not VF minus VD. This is actually supposed to be VF minus VE, which is 2.04, and VC minus VD, which is 0.96. Just note this is VE, not VD. And going back here, record current I, which is 0.02 amps. For 2.7, what should the sum of the individual potential differences be for a round trip around the circuit? It should be 0. And what does it actually add up to? It is 0. For 2.8, we are graphing the potential versus the position around the circuit. Here at 3 volts, we're going from A to B, which is negative 3.00 volts. High to 3.00 volts. From C to D, the difference is 0.96 volts, and from E to F, here, right, it's supposed to be VF minus VE, not VD. It's 2 point. The potential difference is 2.0 volts. When you attach the voltmeter, you alter the circuit. Why does the ammeter reading change? Because 1 over R, like equilibrium, is equal to 1 over R plus 1 over RV. When RV represents the voltmeter. Because the voltmeter has such a high resistance, no current is flowing through it, so ammeter doesn't get affected, because this is just goes to 0. So 1 over REQ is equal to 1 over R. And connect the voltmeter across the 100 ohms resistor again. The ammeter is still 0.02 amps. And what happens to the current through the other ammeter when we put this ammeter as parallel to the 100 ohms? It increases to 0.06. This is due to the other path having less resistance, which is allowing more current to flow. For 2.12, from your potential difference measured from part 5 and 6, and current measurements in part 6, calculate the resistance of each of the following circuit elements, delta V over I. Here for resistance 47, we have 48 ohms, and for R100, we have 102 ohms. For R wire and R ammeter, negligible, so it's just 0. For part 3, the RC circuits, we observe the light produced by the 10 ohm bulb. What happens to the light? The light turns on initially, then fades over time. And what happens if we disconnect the battery and connect the capacitor directly to the 10 bulb? The light turns on initially, then fades over time. It's the same thing. When you first connected the battery to the capacitor and 10 bulb, the capacitor was charging. What happens to the current in the circuit? The current decreases exponentially over time to 0. So when you remove the battery from the circuit, the capacitor began discharging. What happened to the current on the circuit? Again, the current decreases exponentially over time to 0. And to measure the time it takes in seconds for the capacitor to discharge using the 10 ohm bulb. So when charging, it took 5.8 seconds, and when discharging, it took 8.1 seconds. When charging, I timed it. It took 11 seconds for the 20 ohm bulb, and for discharging, it took 15.3 seconds. Here. For 3.1, we are plotting a 20-second discharge. So plot 20 seconds worth of discharge of voltage versus time on a natural log of delta V over delta V max, versus the T plot here we see it is going down linearly based on the blue dots, and uses to calculate RC. And this green slope represents negative 1 over RC, which is equal to negative 0.16666. Does this computed value agree with the RC value of the circuit in the CCK? So we compute this as RC. We got 6.002 seconds, in which if we just plug this here for RC, which is equal to tau, which is 30 ohms times 0.20 Faraday, we also get 6 seconds, which is very, very close to each other. So yes, they agree. So what if you were doing this lab in real life and use an actual ammeter instead of an ideal simulated ammeter? What's different about a real ammeter, and how would it have affected the circuits you hooked it up to? A real ammeter has some resistance, so it slightly changes the circuits by reducing the current and slowing the charging compared to an ideal ammeter in the simulation. And what if you were doing this in real life and used a real battery to charge a real capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? Explain and discuss why the measured time is different from the predicted time. The ideal model would say the capacitor would charge instantly, but in real life there is always some resistance. So the capacitor charges very quickly but not instantly, so the expected time in real time will be different. So conclusions, we can predict the behaviors of circuits containing resistors in series and parallel. We can use multimeters to measure the actual values of conventional current and potential differences in the circuits. We can examine the behavior of ohmic resistors and capacitors. However, behaviors for circuits are different for ideal and realistic scenarios. Thank you. That is all.